Thank you, Jimmy, and thank you for having me. Sorry for the technical challenges. All right, so this talk is going to be mainly about black holes, right? And as you probably don't need convincing here, black holes are among the most extreme and fascinating, puzzling objects in the universe, and yet they are everywhere. And most galaxies have supermassive black holes at their core, and the most massive stars will leave behind a black hole when they die, right? And because a large, or the majority of stars in the universe are in a binary system, there should also be out there a lot of binary black holes. And systems like this raise several questions, some of which you see written here, right? When did they form in the history of the universe, these two black holes? What role do they play in the formation of structure in the universe? What are their masses? How fast can they rotate? Do they pair with other objects like neutron stars with the same frequency with which they pair to one another? Do they remember anything, or can they teach us anything about the progenitor stars that they come from? Or even more simply, how many of these systems are out there? Now, those are all questions that, if answered, could significantly advance our understanding of the physics and astrophysics of black holes, the role they play in the universe, and hence of the universe itself. Unfortunately, there are also questions which are very hard to address with traditional astrophysics, because, as the name suggests, black holes don't emit light. So every time we, since the 70s, we have observed a black hole, what was really meant is that we saw photons from the disk surrounding the black hole, and from the properties of the photon, we inferred the properties of the black hole, which is great, but not really a direct measurement of the black hole's property. And furthermore, observing black holes, or at least stellar mass black holes, I should say, with this approach in X-ray binaries, implies that we can only see them basically within our galaxy, and so we have a few tens of them, with a few more discovered every year. Luckily, as you know, black holes and neutron stars, when they are in a binary system, emit gravitational waves. This would have been a video if we were not using Acrobat, I'm sorry, but you know how the deal goes, right? They lose energy to gravitational wave emission, hence they get a bit closer. That's a runaway process that eventually results in the merger of the two black holes. All right, so systems like this have been discovered now 10 years ago. We recently had parties and celebrations for the 10th year anniversary by the Twin Observatory of LIGO in Washington and Livingston. The first detection, which I'm carrying with me today in my t-shirt, was two black holes colliding at roughly half the speed of light, 30-ish solar mass each. It was very exciting. Ask me about that day later if you're curious about the non-scientific part of it. Right, another watershed moment happened in 2017 with the discovery of the merger of two neutron stars, now this time with the European detector Virgo. Here also imagine a merger of neutron stars. Luckily, there are people in the audience that can simulate that for you and show it to you later. And this is also the last video I have in this presentation. So far, after this, everything will be smooth. For this particular source, we also saw electromagnetic counterparts, which made it particularly exciting and interesting for the scientific community. Right, and because of the role that gravitational waves can play in our understanding of the physics and astrophysics of compact objects, the pioneers of LIGO were awarded the Nobel Prize in 2017. Ray Weiss at MIT, and Kip Thorne and Barry Barish at Caltech. That's also a good moment for me to pay my homage to Ray, who, as some of you may know, passed away just a couple of weeks ago. And here are some pictures of him with a Nobel Prize medal made of Lego before he won the actual one. And it was a great person, and it would be sorely missed. And of course, the scientific legacy he leaves behind, it's hard to match. Right, and this is a QR code to a pretty nice New York Times obituary if you want to read it. Okay, so where are we? That was 10 years later, a lot of excitement. 10 years ago, sorry. 10 years later, we have gone through 4 observing runs, shown in this plot here. X-axis is years, calendar years. 2016 is here. We are roughly here. And the way we proceed in LIGO and Virgo is that we observe for some months or years, then there is a break for improving the instrument, and then we observe again, and so on and so forth. And each observing run is given an incremental O number. So right now we are at the end of O4. And now during this process, or throughout this process, the detectors have increased their sensitivity. We have, as of a few weeks ago, reported the detection of 218 binary mergers. Most of those are binary black holes, I should say, plus 150 candidates, which we have not published yet, but they've been released in GCN alerts and so on and so forth, in the second and third part of O4, so O4B and O4A. This is shown in this plot here, where you see on the x-axis the hypervolume surveyed by LIGO, Virgo, and KAGRA, and on the y-axis, the cumulative number of detection. There is some Poisson uncertainty to show you that things progress as we were expecting. And we are, in terms of published data, at the end of O4A. So basically here, 218. If you read our papers, you may see different numbers. The reason is that, there is some degrees of freedom on what threshold you use to call something a detection, and that affects a bit this number. Again, ask me if you're curious or concerned. Okay, so of these 218, mostly binary black holes, hence the focus in my talk. We had a couple of binary neutron stars and 6 neutron star black holes. Now, each of these systems, taken one by one, of course, can teach us a lot about its history and the properties of the two objects, because those are encoded in the gravitational wave signals that we receive here at Earth. So I think it's beneficial to give you a very quick summary of what our typical system looks like, if for nothing else than to set up some nomenclature. So we have two objects with masses, spin vectors, and spin misalignment relative to the angular momentum, and we receive gravitational waves at some angle iota. Now, ideally, I would love to measure the properties of all of these. I would love to measure these parameters independently with a high degree of precision. In practice, there exist combinations of those parameters that are easier to measure than others. For example, rather than measuring M1 and M2 very well, we measure this combination called the shear mass that definitely you have heard about very, very well. And similarly for the spins, we don't measure individual spin typically very well, but we measure this mass-weighted projection of the spin along the angular momentum, which we call chi-effective, much better. Right. And instead of keep going, let me summarize like decades of research on the characterization of individual sources in this one slide, and where I'm ranking interesting parameters in basically the way they are measured from best to worst. So shear mass typically sub% level for low masses, well sub% for neutron star binaries, and then it gets worse and worse to tens of percents as the mass increase. Next up, component masses, typically tens of percent. Worse when the masses are comparable, which, spoiler, is the average system. Component spins usually very poorly measured unless they are very large, but this effective spin is usually very precisely measured even for massive objects. Tilt angles also usually very poorly measured, and even worse for eccentricity, which can be measured basically only when it's really large. So this seems to depict a rather grim picture. However, we are now in a situation where we have detected hundreds of sources, and so even though taken one by one, some of them may not be very informative on individual parameters, we can combine all of them and learn something about the underlying astrophysical population or populations that those sources come from. And it would help in doing so if we had an idea on basically what to expect, what are the options, what are the possibilities. And the answer to the question, it's rather complicated. It used to be much simpler, paradoxically, before 2015. And if back then you had asked your favorite astronomer what are the ways in which you can form LIGO-Virgo-KAGRA binary black holes, they would have told you probably either of two things, formation through something called common envelope in field binaries, or dynamical formation in globular clusters. I'm going to describe either of these in turn very quickly. For formation in field, the picture and the story goes like this. We're thinking of a galaxy pretty much like the Milky Way. We have two massive stars, which are already in a binary system. Then as they evolve, the first one gets puffy, accretes material into the companion, leaves behind a black hole, then the opposite happens. And there is a critical stage, or there could be a critical stage here, where both of the two objects are surrounded by a common envelope, which shrinks the orbit in such a way that when the second star becomes a black hole, the two black holes are close enough that they can spiral in an Hubble time. Now, there is a lot of very messy and very uncertain physics going on here. So that's just a very high-level cartoon of what could happen. The other extreme, it's dynamical formation in globular cluster. Globular clusters are very small collections of stars typically around galaxies. They are known to host all the stellar population. If you zoom in on one of them, it looks like a spherical collection of a few hundred thousands or millions of stars. And the key point here is that two entry-body interactions can form binaries with very short in spiral time scale toward the center of the cluster, where the most massive objects will very quickly basically sink. Right, that was pre-2015. Now the menu is much, much longer. When it comes to field binaries, it has been suggested that maybe not both of those mass transfer episodes that I've shown earlier in the cartoon are unstable. Maybe they can both be, or either of them can be stable. Or maybe the progenitor stars may not have been needed to exchange mass in the first place through a process called chemical homogeneous evolution. On the dynamical formation scenario, it has been suggested that maybe globular clusters are not the only relevant sites. There may be a significant rate of mergers in nuclear star clusters or even in the disks of surrounding supermassive black holes. And I just had a conversation about this with one of you earlier today, even though it's only 11 a.m. Very good. So how do we find out where our binaries come from? Well, theoretically, what we have to do is very easy. Theory and numerical simulation predicts the properties of those black holes depending on their formation scenario. So all we have to do is to compare those predictions with the properties of the binaries we are now finally detecting. And there are a couple of caveats. One of them is that those numerical relativity simulations are very costly and don't capture all the physics, which implies that we don't have a lot of them and we should not trust them to an infinite degree of accuracy. In spite of that, you can try to play this game. This has been done in the last few years. For example, in this paper led by Mike Zevin, they took models from this population synthesis code for 5 formation scenarios: common envelope, chemical homogeneous evolution, stable mass transfer, globular cluster, nuclear star clusters. They parameterized the output of these codes by 2 numbers: the fraction of common envelope that is removed by the system, and the black hole spins when they are born, so before any accretion happened to them. And what happens is that if you zoom in one of these grid points, for each of those 5 formation pathways, you have predictions, for example, for the shear mass or the chi effective or whatever, and you compare those with the data. More recently, I should also say this has been done with machine learning interpolating through the grid points. So this has been done in O3A data, and it was found that at least 2 formation scenarios are needed to explain the O3 data. And of course, when I saw this paper, and when we all saw this paper, I think a lot of people, including me, got very excited and start wondering whether that's the way forward to the future. And the answer is that maybe we're not quite there yet, because there are, again, several challenges connected with this approach. Some of those were explored in a paper led by April Cheng, who is now a student here. You're very lucky, when she was an undergraduate at MIT. What she has done is to show that the 2 main limitations in this approach are the fact that the astrophysical models are rough approximation of reality, and even more simply, that we may not even have a complete collection of the possible formation scenarios. And what April has shown is that those limitations can introduce significantly large biases, larger than our uncertainties. And this is maybe why in LIGO-Virgo paper, we, as of now, don't follow this approach as our leading way forward in doing population inference. So what else can we do? Well, another way is to use phenomenological models, which is really a nice way of talking about functions that you can parameterize with a handful of knobs. And those phenomenological models might be inspired by astrophysical expectations or geometrical consideration. For example, probably the easiest example is the mass function of black holes. In the first few LIGO papers, we parameterized that as a combination of a power law and a Gaussian. And the reason why that is so is because we know that the mass function of massive stars that black holes come from, it's roughly a power law. And we expect there to be a pileup of masses due to pulsation pair instability at 60, 70 solar masses, who knows. And so why not using a model which is the sum of these two terms with some unknown slope, unknown minimum and maximum, unknown mean of your Gaussian and branching ratio. I should also say that this model has been first proposed by Colloquium Talbot, who is in the audience here. So thank you. All right, so the idea then is that you have this function which is parameterized by 6, 7, 8 parameters, and those are the parameters that you measure from the data. I'm skipping a ton of details. Of course, you can read, like I wrote 50 pages of a pedagogical paper during COVID that explains how this is done, and Colm has his own paper, the LIGO has a lot of papers. So there's a lot of information out there. Ask me if you're curious. Great. The last approach I want to discuss, which solves some of the caveats of this, which mainly are the fact that here you are using a very strong model. And if your strong model is wrong or not perfect, your inference will be accordingly not to be trusted. And so another avenue is to use agnostic models that could theoretically capture more complicated distributions. There is a very long menus of the way this can be done. For example, you can use splines either by themselves or as a mixture with a stronger model, for example, as shown here, where in this paper by Bruce Edelman, they used a model which was the sum of a strong power law and an agnostic spline around it. You can use autoregressive model, your favorite ML approach. New ideas are popping up on the archive every day. Great, and so these last two approaches, phenomenological and agnostic models, are the ones that are currently mainly being used in LVK papers, so are the ones I'm going to discuss a bit more the results of. Okay, so I want to say up front the results from the GWTC4, so as a reminder, up to this block here, are altogether north of a couple of 100 papers. There is no way I can possibly cover this all unless Jimmy gives me way more time. Are you? No? Okay. And I should also say, I'm also not going to discuss results produced by a pipeline developed here at IAS. I see Matthias in the audience. They recently had a very nice paper where they discussed their searches that includes higher order harmonics, which the LBK is not doing currently. But luckily for you, you have the experts here. So you can just go and knock at the doors. Silvia Bescoverno is one of your latest faculty, maybe the most recent, and she's one of the world experts of LIGO-Virgo-KAGRA data analysis and astro interpretation. And Matthias, of course, has been one of the people behind the development of the IAS pipeline. So I'm sure they will be happy to address any point I don't cover. All right. So let me then start with the LVK results. The first thing I want to show is what our full spectrum distribution of masses looks like. Full spectrum means including neutron star, black holes, everything we have detected, okay? Not only focusing on black holes. Those plots are rather complicated. I'm going to take a second. Both of them show on the x-axis the mass in solar masses. So left is 1, right is a couple of hundreds. Y-axis is, x-axis for the primary, most massive. Y-axis for the secondary, least massive. Forget about the blue part of the diagram. That's the fractional uncertainty. We don't care about it for today. The orange and black part, it's representing our measurements of the merger rate in sources per gigaparsec cube per year. And the reason why I have two of these plots is because, again, remember, we're using this strong model and this more flexible model. And it's good to check that they kind of give you more or less the same picture. That's why very often I will show results that have both a strong and a weak model. And in this case, they kind of do with different type of resolution and small uncertainties that depend on the assumptions that are behind those plots. If you squint, you probably, especially in the flexible model part, you may notice 3 islands where the rate is a bit higher. This one here, which is for objects between a few and a few tens or hundreds of solar masses, those of course are the binary black holes. And here you have a light with the heavy objects, those are the 6 neutron star black holes. And here you have the 2 neutron star binaries we have detected so far. And everything else you have lower rates as of now, of course. These plots are pictorially very nice, but not very informative because it's very hard for me at least to distinguish 1000 from 500. So we can take slices or projections of these plots on the M1 and M2 plans planes, sorry, and this is done here. The top panel is for the primary, and the bottom is for the secondary. In both plots, the vertical direction gives you the merger rate in sources per gigaparsec cube per year, per unit mass in this case. So what do we learn out of these plots? First of all, both the strong in orange and the weak model in blue, median as solid line and 90% uncertainty as bands, agree that the overall peak of the merger rate is between 0 and 2 solar masses, or 1 and 2 solar masses. Those, of course, are the neutron star binaries. Then there is a secondary peak at around 8 to 10 solar masses. This is the peak for the mass function of black holes. And I can talk a bit more about what happens to the right of that. But the important thing here is that the rate in between those two peaks goes down, but it does not go to 0. And that is interesting and non-trivial because electromagnetic observations in the last few decades have suggested that there might have been a possible mass gap in the mass function of compact objects between 2 and 5, 6, 7 solar masses. And what we are finding with the LBK data is that that is definitely not the case. The rate goes down, but it does not go, or is not consistent with going to 0 as shown in this inset here, which I can discuss more if people are curious. So that's great. And we started learning something which is useful and potentially a bit in tension with what we thought we knew. The other thing that we can do, since most of our sources are binary black hole, it's perform analysis which are dedicated to the binary black hole populations. And one of them, it's again about the mass distribution. And so here I'm only using black hole binaries to perform my inference. I'm throwing away NSBH and binary neutron stars. And here again, I'm showing the mass, the merger rate as a function, in this case, of the primary mass. But this time I'm going, unlike the previous plot, to much heavier objects. I'm stopping at 100 solar masses. Again, you have a couple of sets of color curves. One is a weak model and another one is a stronger model. I can talk details if people are curious. The big picture is that, again, we find this overall peak for binary black holes at roughly 10 solar masses. And then both approaches agree that there is a secondary peak at 35-ish solar masses. And something new compared to the previous data release, at least for LBK analysis, is that we might start to see a hint of another bump here at 20 solar masses. This was already discussed as a possibility in some short order non-LBK work, but now it's popping up in our analysis too. The other interesting thing, and that is shown even better on this plot here, is that if I ask myself what is the slope of the continuum outside of these two peaks, and so if I use a model that allows for these two slopes to be different, well, they do not want to be the same. This is shown in this inset here that shows you the slope at the low mass side and the slope in the high mass side. Diagonal would be those are the same, and you can see with slightly different values for different data sets that they want to be different. And that's interesting because the slope between the first and the second peak is consistent with the slope of the massive progenitors, the massive stars progenitor, so like Salpeter, but the slope past the 35 solar mass peak seems to be steeper, which may be one of the hints that we are gathering from this data set that we have more than one population that we are observing in our data set. All right. I should also say that here I'm stopping at 100 solar mass-ish. Something more exciting, something very exciting happened at even higher masses recently. We published the detection of this exceptional event, 231123. The reason why this is exceptional is because it's very, very massive. It was found to have a primary mass of 140 and a secondary mass of 100 solar masses, which would make it the heaviest object we have seen. And the reason why that's astrophysically interesting is because the common understanding in the mass function of black holes, shown in this cartoon here, is that we have stellar mass black hole between 10 and 100 solar masses, and the supermassive black holes of millions and billions of solar masses. And in the middle, there should be so-called intermediate mass black holes, but on the EM side, those have never been found with certainty. And now we maybe start to probe this region from the left side. It was also, this particular source, interesting because the spins were found to be very high, 90% of maximum. And both of these things, both of these properties make this object very hard to explain with standard formation channels. A possibility is that this could be a hierarchical merger where the merger we have seen was in turn generated by a previous generation merger. And I'm not going to talk more about this because I'm already late, but here again, you have people here, here is like globally defined, like Jenny, who work on IMBH and the role they can play in the formation of supermassive black hole as seeds early in the history of the universe. Very good. Let me now move on and talk to spins, which is admittedly the only other property we can measure from a black hole. What we find, which is consistent with our previous data sets, is that the black holes in the populations are, the black hole spins are found to be small. This is shown in this plot here, where on the x-axis I have spin magnitude. 0 means no spinning, 1 means maximal in our units, and the y-axis is just the probability. Red/orange is the strong model, which is a truncated Gaussian. The bluish is a weaker model based on splines, and the empty, it's the old result. So what we found, irrespective of which model you use, is that our posterior probability peaks at 0 to 0.2. So rather small spins. And this finding has been, over the last few years, since this is consistent with our GWTC3, has been, resulting in a lot of theoretical work in the community to explain why and how black holes can be born with basically close to 0 spin. I should say the way this result is produced, it's using a rather strong model where both of the black hole spins come from the same underlying population, and that population is parameterized as a truncated Gaussian. Another approach that you can follow, which was pioneered by Sylvia, is to ask the data a slightly different question, and instead of measuring the data, the spin of the heavier and lighter object in the binary, is measure the spin of the most spinning and the least spinning black hole in the binary. And if you do so, you obtain the results in this plot here, where, again, we have medians and 90% uncertainty. Chi-A, the distribution that peaks at 0.3, 0.4, is the astrophysical distribution of the most spinning objects in the binaries, and Chi-B is the least spinning black hole in the binary. And so what we find using this approach in the latest LBK data is that the most spinning black hole distribution peaks a much higher value, 0.3, 0.4, while the least spinning black hole distribution is consistent with basically being 0. Now, either way, whether you perform this analysis or the other analysis, we are finding results which are rather different than the spin distribution measured in X-ray binaries, which by itself is a very interesting finding, and there has been a lot of paper in the literature trying to explain whether that's a problem or not. Okay, fantastic. Yes, of course. Sylvia will tell you this at the coffee after this. Okay. Yeah, because you are basically sorting them. Yeah, so yeah, it would be. Yeah, absolutely. And I should also say that Sylvia has recently written a paper where some of these answers and more are provided, I hope. Yeah, very good. Okay, fantastic. Now, the other degrees of freedom of spins that we can measure is the orientation, right? What is the spin vector? How is the spin vector oriented relative to the angular momentum? The reason why that's interesting is because, at least broadly speaking, that gives you information about the formation scenarios of the two black holes. And the reason why it is so is that formation in fields, so the scenario where the two black holes were two stars already in a binary, is expected to yield black hole spins which are roughly aligned to one another and to the angular momentum. So this is the picture you have in mind: stars, black hole, spins roughly aligned. At the other end, dynamical formation, irrespective of where it happens, should result, artistic clusters, should result in isotropic spin distributions because no direction is preferred. Okay, so at least we have these two pretty extreme different expectations, and we can fold them in the model we use to measure the distribution of spins and orientations. So this has been done in the latest LVK paper using a strong model actually I proposed a few years ago, where improving a model that Colmas proposed before me, where basically our distribution is assumed to be the sum of two terms, an isotropic term that captures dynamical formation, and Gaussian terms that captures possible preference of a line system. And critically, the position of this Gaussian, it's allowed to be whatever it wants. It's measured from the data. This is the blue model here. X-axis is the cosine of the spin angle. -1 means anti-aligned. 0 means perpendicular to the angular momentum. 1 means aligned with the angular momentum. Y-axis is the probability of the cosine. So blue is the strong model. Orange is a weak model based on splines. And the empty band is the old result from a GWTC3. Now, irrespective of what model you use, you're getting that the data does not want to give you a posterior that picks a 1, which is what you would have expected if a significant fraction of the black holes we are detecting are forming in the field and hence add preferentially aligned spins. In fact, they want to pick at around 0, 0.2, 0.3, 0.4, whether it's a strong peak or a plateau, that does depend on the model. And so is this concerning / exciting? Does this point to new astrophysics that our friends that do population synthesis or supernovae kicks are not thought about? And the answer is that it's probably not yet the case. The reason why I'm saying so is that in a recent paper, we have simulated our way through this basically astrophysical problem and shown that even if the true astrophysical distribution does have a peak for a line spin, you may get, with catalog sizes comparable to the one we have now, or even larger, you may get spurious peaks away from unity. This is shown in this very complicated plot. I'm not going to go through all of this, but the x-axis for all of these insets are always the cosine of the spin angle. So there's a one-to-one mapping between this plot and those plots. And the y-axis are the measurements. Different rows are number of events. So the first row is a catalog like the previous data set. The middle row is a catalog comparable to this data set in size. And this is like the future, 300 sources. Yeah. Yeah, I'll tell you why in a second, okay? So there are several caveats, but it goes as follows. Let me first finish my thought and then I'll go back to this. So in these simulations, the truth is this blue curve. So it's a pretty broad, sum of an isotropic distribution in the Gaussian that picks a 1. The dash and solid pink are median and 90% uncertainty, and the small dotted are the priors, okay? And if you take, for example, this panel here, which again is 150 sources, very comparable to what we have now, I'm getting a very broad plateau that looks very much like this red plateau here, right? And so that's why I'm saying that I don't take this as necessarily implying that there is no peak at 1. Now, to your question, the red curve, the red band allows you for a very shallow peak at 1, which is possible because that will depend on the width of the distribution, which depends on the supernovae fallback pretty much, right? One may argue that the blue distribution is maybe less consistent with that, okay? Although yes, maybe a small peak here. Of course, the blue distribution assumes splines, which are a much more agnostic model, so they may be more sensitive to Poisson noise and these kind of things. But yeah, I guess what I'm saying is that this measurement is really complicated. By the way, we deduct this from question time. Jimmy, looking at you. Because we measure these tilts very, very poorly. And so what we have shown in this paper, and I'm happy to chat more about this later if you want, is that even with catalog of 150 sources, you may have or not have 1 or 2 or 3 more informative sources that happen to be or not be in your catalog, and that can significantly drive the inference pretty much, okay? And again, happy to say more about this. Okay. The last thing I want to say about spins is chi-effective. I told you we measure chi-effective better than either chi1 or chi2. And so this is shown in this plot here. X-axis is chi-effective. It doesn't go all the way to -1. If -1 were here, it would mean both black holes have anti-aligned maximal spin. 0 means that either there is no spin magnitude, or if there is spin magnitude, it's perpendicular to L. And 1 means maximal and aligned. Okay, just to give you a physical picture of what's happening, and y-axis is the probability. This is obtained with a Bayes model that assumes the underlying distribution is a skewed Gaussian. Okay, so we are measuring the location, the width, and the skew parameter, which actually is measured to be non-zero 99.3% credibility. This is the blue median and 90% uncertainty. The empty dashed band is the old result. So we get something that peaks at or around 0, but has a fatter tail on the right and on the left. And this also, it's potentially suggestive of there being more than one formation scenario. Why? Because if all of our black holes were formed dynamically, I would have expected a symmetric effective distribution around 0, because all directions are equivalent. And here I'm getting that there are more black holes with positive spins. In fact, you can measure these numbers and you obtain that no more than 84% of the sources can come from a dynamical channel, which is interesting. Very good. Now, so far, all I have described mostly assume that my mass and spin and redshift parameters were statistically independent from one another, right? So the mass distribution didn't know anything about the spin distribution. And in reality, of course, there are good reasons to believe that the underlying astrophysical processes that are creating those sources will somehow couple or might somehow couple masses and spins and redshift. And now, of course, as our data set is growing in size, it starts being more and more doable to go after those correlations and try to measure them from the data. So you may have heard of two such correlations. One is a purpose correlation between mass ratio and chi-effective. This was reported a few years ago in a paper led by Tom Callister in GWTC2 data, so that's pretty old data. In this paper, we showed that if you allow for a linear correlation between mass ratio and chi-effective, the data tells you that chi-effective should be higher for smaller mass ratios. This finding was later corroborated by other people using weaker models, and which are, if you're interested, copulas, and more recently also with splines. Those analyses have been performed again in GWTC4, and the picture has somewhat changed. That's why I'm talking about it here now. With the latest data set, it is not as clear whether it's the mean or the width of chi-effective that are evolving with the mass ratio. This is shown in this plot here, where on the y-axis you see mass ratio, equal mass is here, very unequal mass is here. This is the mean of your chi-effective distribution as a function of Q. This is sigma. The orange median and band are for a strong linear model, and blue is splines. And what you can see is that maybe there is some evolution, but it's not obvious if or which of those two are evolving. It's better to look at this problem in a 2D plane where you plot basically the slope of the evolution with in the mean and the evolution in the width. That's what I'm showing here. Those are the 90% uncertainties. And what you can see is that if there were no evolution whatsoever, your posterior should be here at 0, 0. And the linear model definitely is ruling that out at very high confidence, higher than 99%. The confidence is somewhat lower for weaker models, as you would expect, because their uncertainties are larger. So the picture here got a bit more fuzzy about what is happening. I should also say that when this was first found, it was very exciting, especially for people working on AGN, because AGNs, this could be a way of creating this correlation. Another correlation which was actually found by Sylvia, it's between chi-effective and the redshift. So in this letter paper a few years ago, Sylvia showed that using GWTC3 data, the distribution of chi-effective broadened as you go past farther and farther in redshift, while the position did not evolve. And there were a few, or actually several interesting theory papers that explain why you may have expected that, due typically to the way metallicity changes with redshift. Now, these findings are confirmed in GWTC4 using both a linear and an agnostic approach. I have the plots here. Redshift on the x-axis, we are here, very far is here. Top panel is for the mean of chi-effective, bottom panel is for the width of chi-effective. Strong model in orange, agnostic model splines in blue. You find that the mean doesn't seem to be evolving at all, but the width does increase as you go to higher redshifts. There, of course, are differences, as you may expect. I'm happy to comment more on this later, because the linear model is a very strong model, so it will extrapolate farther from the redshift where most of our events live, which is shown by this dashed line. But the broad picture, a smaller redshift, is that we seem to get wider chi-effective distribution. On the redshift, we're talking typical of tens of %. Yeah. Absolutely. That is accounted for in the analysis, of course. The analysis knows about it. I should also say, thank you, that's a non-trivial point. Because when we found these things, some of those findings were surprising. Everything has been basically also tested in software injections where you know what the truth is because you simulated it, and so you can check, for example, that you're not fooling yourself just because the uncertainties are bigger and other things. I'm happy to discuss that. Yeah, I don't have that in spare slides, but I think you would believe it. Yeah, yeah, I believe this more than I believe other things. You know, as a data analyst, I typically ask myself, would I bet on something? The odds ratio, like a coffee, my house, and my life. This is a good dinner, you know, like 2 Michelin stars restaurant, something like that. Okay, very good. One thing I want to advertise, just because I think it's really, really cool, is some recent work at MIT that we have been developing, and that is I'll first read this, but it's a mouthful, and then I'll tell you what I mean. Software to perform high-resolution, high-dimensional agnostic population inference. And the reason why this is important and what it means is the following. High-dimensional, well, because those correlations may live in the full parameter space. Masses may be correlated with spin and with redshift and with chi-effective, right? But a lot of or most of the results I've shown so far, for simplicity, because they just model a pairwise combination. But we would like, ideally, to allow for everything to be correlated with everything eventually. The other thing, high resolution, is because, as I've shown you early on, one of my plots was very, very sketchy, at very big bins and very large error bars. And so to me, we need to be able to resolve very small features now that the data is bringing us to the region where we have hundreds of sources. I should say, so these analyses are not in GWTC4. We are writing our own paper to show what it can be done. And just to give you an idea, this is the plot to compare with the one I showed you very early, where this part here of the histogram with an agnostic approach had bins that were very, very big. Here you have a much higher resolution, so you can resolve small features. And if you project this to the primary mass plane, for example, 10 minutes, okay, should be good. You get a plot like this. So this is basically the one I showed you before from the LVK paper, where the orange is the strong model for the full mass spectrum. The blue was the weak agnostic model in the LVK paper, and the green is what you obtain with pixel pop. And I think the point I'm trying to drive here is that it's much smoother than the blue. The uncertainties are much more continuous and well behaved just because the resolution is much higher. And the other exciting thing about pixel pop, going back to the topic of testing that your models work when you know what the truth is, we have applied it to simulated signals that were drawn not by my brain, like an agnostic simple distribution with power laws and Gaussian, but rather drawn from population synthesis output. So basically what we have taken in this paper, led by Sofia Alvarez Lopez, we have taken a few hundreds binary black holes produced by common envelope, pretty much, as described by Compass, I think. And for example, those population synthesis codes tell you that the primary mass and the mass ratio of this binary black hole should be highly non-trivially correlated. This is shown in these contours here, 50 and 90% of the sources. If you did 99%, it would really look like Cape Cod, it will go high. And then you see the marginals. The truth is the white dashed line, and the blue greeny measurement here and the orange measurement here are what you obtain with pixel pop. And as you can see, we can measure very well both the joint and the marginal distribution. There is some discrepancy in some regions. I'm happy to tell you why you should not be worried about that. So I'm very excited about this because, as to my knowledge, is the first time correlated population analysis have been shown to give you unbiased results on a population that is based on PopSynth, not on heuristic models. And I should also say we can run these as of now up to 3 correlated dimensions and working on the 4th. Another thing I would just very quickly mention, because I don't want to pick up fights, is that recently, as of a week ago, you may have heard of this new event. Actually, I don't have the phone number, maybe it's on the next slide. So this was published just a few days ago. It's a binary black hole, which is basically the louder twin of 15914. Very conveniently, we published this 10 years later. The total signal-to-noise ratio is 80, which is really, really loud. Like back then, for like 25, we didn't believe it was real, and now we have 80s, right? And now this is so loud that the ring down part only, I mean, I don't need to tell you in this room what the ring down is, but it's the last few cycles after the merger, that's louder than all of 15914, okay? So these allowed for consistency checks between the Erlang spiral and the final black hole properties, and the testing if the final black hole is ringing as you would expect in GR. But for reason of time mainly, I won't go in detail, but once again, I don't need to. You can ask local experts. Franz, of course, will be able to tell you everything about that, and Mark and other people in the audience. The one thing I want to say is that ring down analyses are really subtle. There are very many things that need to go right. So I don't want to make a disservice trying to rush through this. Okay, I also like this photo because it really makes it clear what makes science possible. Okay, so my conclusions are that GWTC4, at least for what comes to LDK pipelines, has doubled the number of known sources and confirmed some results like the peak at 35 solar masses and shown some new features, excesses at 10 solar masses, maybe at 20 solar masses. We have shown the existence of compact objects below 5 solar masses, hence no mass gap. And above 100 solar masses, we have confirmed a dearth of large spin and preference for positively aligned spins, though not all of them are positively and aligned. We confirmed that spins seem to be in magnitude larger at larger redshifts, and the mass ratio pairing, and not talked about this in detail because it takes half an hour, may be evolving with mass, and correlation between chi-effective and mass ratio, even though the exact nature of this is becoming a bit more murky. But I guess to me, what all of this is perhaps suggesting is that we are seeing now finally rather strong hints or clues that our 150-ish sources really are the sum of several astrophysical subpopulations, each of which may have its own properties. And the exciting thing is that I told you this is for O4A. We are about to finish O4C, and that will double again the size of the catalog, in just a few months. So there's a lot of exciting science ahead. For those of you who love neutron stars, I have in the backup a couple of depressing neutron star slides. So ask me if you're curious. Bottom line, no new neutron stars. Thank you.
Colloquium? Yeah, questions.
So you very briefly touched on this, and you have your point here that you have a dearth of large spins, but that's not what the X-ray binary population and AGN for that matter show. Would you like to comment on that a little bit more?
Right, so thank you. So the question is about the disagreement between the spin magnitude measurements with our data and with EM data. And I cannot scroll quickly back because this monitor is dead now. Right, so there have been a few papers that have explored that. The most, like I say, the simplest explanation is we are not targeting the same population. So why would the property be the same? Very obvious, for example, difference is that X-ray binaries, at least, are probing Milky Way stars, while our events leave a redshift, up to 1.5, where metalysis were much lower, and so you would expect the properties of the progenitor stars and the accretions and tides to be potentially rather different. And in fact, I think that is probably the main factor. I am not worried in the sense that I don't believe that we should have expected necessarily those two distributions to be the same exactly for these reasons. I don't have any strong reason to believe that we are targeting exactly the same black holes that we see here in the galaxy. If you think that should be the case, I want to talk to you. And for AGNs, I guess you're talking about the actual AGN, so the supermassive black hole. I guess that's very different because that I think is just an entirely different beast because they accrete. We don't know how they form in the first place. You may have gotten a large spin to repeated mergers, like who knows.
More questions?
I was a little unclear at the end whether you said there's no mass gap at all. That is, we really don't see a diminution at all. Your different graphs showed or did not show that there was a gap. I guess that's the yeah. So what do you really believe? I wasn't quite clear.
No, sorry, I said no. I in my previous statement that there is no mass gap in the sense that the rate here, goes down by say a couple of orders of magnitude compared to the neutron star peak, and maybe one order of magnitude compared to the black hole peak, but it does not go. It's not consistent with going to zero. Okay, so we have definitely seen objects. I can name you some of the phone numbers that have masses that squarely live in this region, so it cannot be empty. And if you think about it, some of the processes that may lead to compact objects in the gap are actually pretty simple. Like if I start from a neutron star binary and I merge the neutron stars, the most likely outcome is a 2.8 solar mass black hole, which is already on the lower end of the mass gap. And that might or might not merge again. There are challenges for making merge multiple times because of kicks and escape velocities. And so I think as of now, this is just my opinion, I'm not talking for the AVK, I should say, more and more people probably believe that the dearth of compact objects here on the EM data is more likely due to selection effects on the EM data side, pretty much, of which I'm not an expert, maybe someone in the audience is. And so they are not being seen, not because they don't exist, but because they were harder to see the lighter and heavier objects.
Maybe one last question. How accurate can we locate those patterns? Is there a way to improve the measurement about their locations?
For the boundaries, you say?
The location of these patterns.
So like here, pretty much in here?
Which part of the galaxy they are?
Oh, the binaries. You mean like in the 3D volume? Well, okay. That is the part where I'm not happy and being recorded. So let's see. If you take a single gravitational wave detector, it basically gives you no information about sky position, right? So you need to triangulate. You need at least 3, ideally 4. And now, because of a series of technical challenges between O3 and O4, the detector in Europe, Virgo, did not make it to the sensitivity that we were, expecting / hoping, and they're still kind of catching up a bit. So that means that our typical sky location uncertainties right now are bigger than what we would like. So, say hundreds of square degrees. Not all of them. If you subscribe to the GCN services, you will see we have released a few events with, a few tens of square degrees, so reasonably well localized. The only way you can make this better is A, you're very loud and you get again another 17 by 17 at 40 megaparsec. I'm not holding my breath. I'm sorry if you work on star binaries that close, it's going to be very unlikely to get another one like that very soon. Or you add legs to your network. And so we need Virgo to become even more sensitive, and we need another detector. And that means either KAGRA, which is a detector in Japan that is already been built. It's a 3-kilometer cryogenic detector in the Kamiokande mine, pretty much. And they too have hit some limitations, mainly driven by the fact that they have pioneered a lot of new technology because they're cryogenic, so they cannot use the same mirror, they cannot use the same coating, they cannot use the same laser. And a lot of things that could go wrong went wrong. And so they're a bit behind in sensitivity. They're not really contributing sky location right now. Hopefully they will in the near future. And then there is a new detector being built in India, called LIGO India. When I say being built, what I mean in this context is that they have acquired all of the land they need. So there is a site, they own the place, and they're starting to build some of the infrastructure, but we're talking of years time scale for that.
Okay, so Salvo will tell us more about gravitational lunch, so we can thank him.
Thank you. Go ahead.